the energy of a partition PU and partition PW is just the sum over pairwise sets, UI and WJ. And now you can define the energy of partition. The energy of partition, Q of P, by definition you can say Q of P and P, and this is equal to I from 1 to M, J from 1 to M, the energy between VI and VJ. You sum all of that. So now we want to prove that energy never decreases under refinement. And the lemma 1 that we need for the proof of Szemerédi lemma is that the Q of PU and PW, because we have done a refinement. Because we have done a refinement, we want to say this any refinement just increases the previous clustering. I mean, you have a partition, you have a set U, and we have a set W, and you partition them. They partition them. And we call this P of U, and we call this P of W. For example, let's define a random process. For example, now X is inside UI, and this is UI. And pick a random variable. I mean, just choose it randomly. Tick randomly. So this is so we have selected this partition, this cluster. And so the random process that we have defined is that we have a random variable Z such that it is the density between UI and WJ. So it is the edge density between UI and WJ. And I said that you pick it randomly. You pick X randomly, and you pick Y randomly, uniformly from W. Okay, now because X and Y, because you have picked them randomly, you look at which cluster have you chosen. For example, if you choose X here, then you should say, okay, the cluster UI is selected. You randomly pick Y and say, okay, cluster WJ is selected. And WJ is selected, UI is selected. Now you calculate the edge density between those two clusters. And this is the variable Z that we have defined. And now if you want to use Jensen inequality, because x squared is a convex function, then we can use the Jensen inequality and use the easy inequality, that expectation of z squared is greater than expectation of z squared. So by convexity, you can easily say that for any random variable z, so this is a random variable because we define a random process. So we can say that this inequality holds. And now we want to say what is this and what is this, and then you use the inequality. And E of z is very simple, because you first write the probability that x lies in UI. What is that? It is the cardinality of ui divided by u. So this is the probability that x lies in u. So the bigger the cardinality of ui, you have a bigger chance that x lies in ui. The same thing, because they are independent, you pick x randomly and then you pick y randomly, they are independent. They are not dependent. So for the same argument, I would say that this one is like this. So until now, these are just the probabilities. Probability that y lies in wj. Until now, it is the probability. And because we are calculating the expectation of z, what is z? Z is d of ui and wj. And if you just do this, you will realize that this is nothing else but the edge density between u and w. This is nothing else than edge density. So we call it d of u and w. Now, it suffices to calculate EZ2, expectation of Z2. So let's see what the second moment is. The first term is the same as usual. The probability that y lies in wj is this. And then, but now we have z squared, not just z, but it is z squared. So d of ui and wj squared. And if you work on this is just times q of pu and pw. And then by convexity, we say that this holds, and our lemma 1, that the energy of a refined partition increases, is now complete. So let's move on to the second lemma. I just declare it, and I don't prove it, because for the proof we just apply lemma 1 to every pair of parts. So lemma 2, because it's easy, I don't prove it. If p prime refines, so it increases energy, refines p, then the energy of p prime increases. And the proof is simple. Just apply lemma 1 to every pair of parts, q, vi, and vj. So it is very, very easy. The lemma 3 is the last lemma that you need to prove. Lemma 3 and lemma 4 are the last lemma that you need to prove Szemerédi lemma. Szemerédi lemma. So lemma 3 is, they call it energy boost. So if u and w is not epsilon regular, as witnessed by u1 subset of u and w1 subset of w. So u1 and w1 are not epsilon regular. All the rest of the subsets, the rest of the pairs are epsilon regular except u1 and w1. Then we can say that the energy of u1 and u excluding u1 and W1, W excluding W1. This is at least the energy of U and W. What is missing is just epsilon to the 4, cardinality of U, cardinality of W, divided by n squared. So again, like the arguments of the previous lemma, the proof of the previous lemma, we can say that the variance of z is equal to Ez squared minus E of z squared. And this is equal to n squared divided by cardinality of U, cardinality of W, Q of that things minus Q of U and W. And the same thing for variance of Z, we can say that the expectation of Z minus E of Z squared, which is greater than U1 U, W1 W times D of U1 and W1 minus D of the density between U and W squared. And this is greater than epsilon. So by definition of epsilon regularity, we can say that, okay, the first term, the second term, the third term, so epsilon, epsilon, epsilon 2. So this is greater than epsilon 4, and the proof is now complete. And the last lemma, lemma 4, that you need to prove Szemerédi theorem. We call it Szemerédi theorem because you can use it in different contexts, and nowadays it is a very, very popular theorem. Lemma 4. If partition P, you can write the vertices as the union of V1 up to Vk is not epsilon regular, then there exists a refinement Q, whereas every Vi is partitioned into at most 2 to the k parts, such that Q of Q is greater than Q of P plus epsilon to the 5. The proof is very simple because we want to find those witness sets. So for any I and j, such that the pair Vi and Vj is not epsilon regular, same as usual, we find those that are witnessing it. It means Ij, Vi, and Aj, I, Vj. That witnesses that irregularity. And the Q, it's just a common refinement by Aij. So by lemma 2, we can say that this is greater than Q of Vi and Vj plus Q of Aij, Vi excluding Aij, and Aj, Vj excluding Aj. And now we just need lemma 3 to say that this is at least energy of Vi and Vj plus, we have proved that if it is not epsilon regular, we can write it is at least epsilon to the 4 Vi Vj divided by n2. And this one is just less than, let's say, epsilon n2, using just definition of epsilon regular partition. And finally, this is greater than Q of partition plus the remainder is epsilon 5. And the proof is now complete. And now we are ready to prove the Szemerédi lemma. Serendipity, Szemerédi, I always confuse all these things because I watched cartoons very much when I was a child. Szemerédi, regularity, lemma. So we start with trivial partition, very one large set, and we repeatedly apply lemma 4, whereas the current partition is not epsilon regular. And you see that Q of P increases by at least epsilon to the 5 in each iteration. So it's very dangerous because it grows and grows. We stop after epsilon minus 5 steps. And this one would result an epsilon regular partition. And the proof is now complete. But the big problem, big challenge is how many parts. You cannot just do a clustering and say you have thousands of clusters. You have exponential number of clusters. So how many parts? So if P, your partition, has K parts, lemma 4 is just refining it. So lemma 4 refines P into at most K2 to the K, and you can write another inequality as well because this is greater than that. And so the final number of parts is at most 2 to the 2 to the 2, and the tower of that is at most 2 epsilon minus 5. And now we want to talk about application of graph Szemerédi regularity. I mean, you can use it for the proof of Erdős-Stone. And so the problem is, how does the global parameters such as edge density, for example, edge density, which is equal to number of edges, number of vertices, choose 2. So these are global parameters, either chromatic number or edge density. So we want to see how can they influence local so these are global parameters, and we want to see what happens as opposed to local parameters, like for example, what can we say about local structures, such as does it contain KR subgraph? So does it force? Does the global nature forces local nature? Does the global nature forces local nature? So this is extremal graph theory. Does the global parameters influence local parameters? And a very good answer is, again, Erdős 1946. So I just repeat it because I've written it before. For all r greater than 2 and s greater than 1 and epsilon greater than 0, there exists an integer n naught such that every graph with n greater than equal to n naught vertices and at least the Turan number plus just very small epsilon in two edges contains your complete or apartheid graph with independent sets having